A4 is a fantastic ratio for paper. In fact, the entire A paper scale is pretty incredible. I've got one of all of them here from A1 up to A10. Each one is half the number below it. In fact, I can put these into a spiral. Let's do a spiral. Look at that. So A4 exactly fills in there between A3, A2, and A1. Then we go all the way down to A5, half again, A6, A7, A8, A9, A10. Look at that. There could be more because each one is half of the previous one. If you go the other way, there is, of course, the foundation layer, A0. This is exactly 1 meter squared on a piece of card in the ratio of √2. And because each one is half the previous one, you can always fit a power of 2 of 1 onto a bigger one. In fact, it's the power of 2, whatever the difference is. So you could take A9, look at adorable little A9. Technically, but because the difference between 0 and 9 is 9, you could fit 2 to the 9 of these. You can fit 512 A9s. They would perfectly cover an A0. All of that said, a lot of it's not true. Bunch of that technically just not correct because of a weird quirk in how the A paper scale is defined. You've got other ratios. So not only is √2 not technically correct, at some point you've got 2/3 as the ratio of a piece of A paper. But I'll explain more as I do actually take hundreds of A9s and I'm going to stick them all to this A0. By the way, this video is supported by Jing Street's WISE program for women going into some kind of STEM-related first year of university next year and is running out of the Hong Kong, New York, and London offices. Details below. Actually, as a quick break from doing this, let's talk about why we even want our paper system to be based on √2. So we start with a piece of paper where we're going to call the short edge of 1 with single unit, and then we got x, which is the ratio of what you multiply 1 by to get the longer side. And what we want is to be able to slice this paper exactly in half. And what we end up with down here, this new sub-rectangle, has exactly the same ratio. Oh, which means we need to work out what this is. I mean, that's going to be half of x up there. That's half of x down there. But now we want to kind of reframe this as that being the unit and work out what this is. And oh, well, that's easy because if that's x on 2, if we were to swap them over, I'll do this in green. If that was our newly defined unit for the small one, then this would be, well, the inverse of that. That would be 2 on x. And we want that ratio in green to be the same as the original ratio that I wrote down in black. And so we'll just chuck that up the top here. We want x to equal 2 on x, which means, I mean, you could think about what can you divide into 2 such that you get back that same number again. It's going to be √2. If you really want to go nuts, you can multiply both sides by x. X squared equals 2. X equals √2. So √2 is the ratio, whereas if you half the paper, you don't change the aspect ratio of the piece of paper. However, rolled up in that are a couple of assumptions. There are actually 3 different properties we're after for our paper scale, and people confuse what causes what and all this. But the moral of the story is, we first of all want it to be something where you split one piece to get the next pieces. So for example, an A4, you split A4 and you'll get two A5s. So the first property I'm just going to call, it can be split. Secondly, we want the 2 split pieces to be equal. So in the case of splitting A4 to A5, we split it exactly in half and we get 2 identical pieces. And finally, we want the pieces to be similar. That is exactly the same ratio. That's what we looked at a second ago. So if I hold these, I don't know what the correct distance is, but if I hold them the correct, they should look exactly the same because they're the same aspect ratio. They're similar shapes. One is just bigger than the other. Now those are 3 different properties. So for example, you can have a paper scale where you split it into 2 pieces, but the pieces are not equal, but they are still similar. So for example, if you start with a ratio of, and I hate to say this, the golden ratio, if you split it into unequal pieces to get a square and a rectangle, the rectangle is perfectly similar to the original rectangle. It's still the golden ratio. In fact, you can keep unequally splitting it and you always get a square and another golden ratio rectangle, and that carries on forever. So there we've got the split property and we've got the similar property. We haven't got the equal property. It's also possible to split into equal pieces, but they're not similar. That would be if you started with, let's say, a square, and then when you cut it in half, you get two equal rectangles, but they're different to the square. Then you cut each of them in half and you get two equal squares, which are not the same. They're not similar to the rectangle, but actually they are similar to the square you started with. So actually it turns out for all of these shapes, if you start slicing them into equal, so if you keep equal and you always cut them in half, for every other ratio, when you cut it in half, you start flipping between two different families that are interweaved of similar shapes. In fact, here's a fun plot. We have a line for y equals x, and we have a line for 2 divided by x, which is the equation we had on the whiteboard a second ago. And if you pick any starting ratio of your piece of paper on the horizontal axis, the two values above it are the two aspect ratios you will flip between if you continually dividing them into equal halves. And where they cross is the only place where there's only one value, and of course, that's exactly where root 2 is. Oh, by the way, so I was chatting to my friend Eliane McDonald. We were on the train home from one of my recent Getting Triggy tour gigs. Link to the October shows in the description below. And we realized, you know, people confuse the splitting and the similarity and the equal and all this stuff. So we came up with those three properties. And then when I looked at the official ISO definition of the A4 paper scale, they have those three properties. They're actually defined. They have the fact that they have the halving. They call it the halving principle, they've got the proportionality principle, and they've got the similarity principle. So we were just messing around with it, but it turns out we came up with the same three rules that are in the official spec document. Although Eliane did want to add one more important property, is that they're able to make a cool spiral.
So these are equal. Two of these does equal one of these in area. They are definitely similar shapes, but I cannot fit two of them onto one without an overlap.
To see more of Eliane's excellent work, do check out her channel where, there's an update for our bridge height sign challenge from my previous video. But anyway, that's a whole separate thing with nothing to do with A4 paper scales. So, what about other paper scales, you say? Well, the A paper scale is basically the only game in town. There is also the B paper scale, but that's exactly the same. It's the square root of 2 based paper scale, except instead of starting with A0 being 1 meter squared, B0 has one of the lengths as exactly 1 meter. So the B scale just starts with a unit length being a meter. The A scale starts with a unit area being a meter squared. Oh, and fun fact, the B bits of paper, each one is the geometric mean of the A sizes on either side of it. So if you want a size which is bigger than 1A but smaller than the next one up, you can use the B one in the middle. And C is the geometric mean of an A and the B above it. And they're used for envelopes because they're a bit bigger than the A. So you can fit any given A size bit of paper into the C size because the C size is the geometric mean of the A and the geometric mean of the next A up. Look, the point is it works, and there are 3 different scales, A, B, and C, that all use a square root of 2. They just have different starting sizes, and it's all very, very clever. And that's basically it. That's all the world uses. I mean, there's America. I don't really know what they're doing over there. They're still using, I don't know, a whole bunch of ridiculous. Look, I'm not going to, look, I will say it's terrible, and that's it. I'm not going to get it. Oh, okay, you know what? I will add one more thing, actually. As a member of the A scale team, I would like to say, I pity the fool scap. Oh, wow. Oh, really? Oh, thanks. I know. Finally told a joke. Joke of the year. I mean, it's mine to lose at this point. And that's it for other paper sizes. I mean, no, you can have one-off sizes. Don't start commenting, oh, index cards. You know what? You can make a piece of paper or card any ratio you want. The point is, for a scale of like descending sizes as part of the same family, the A scale is it. I cannot think of anything else that could possibly. Post-it notes, there is one more scale. The post-it note scale is its own thing, and it's super interesting, and they do all relate to each other. I call it the P scale. Probably shouldn't do that. Too late. Obviously, I did some looking into this, and I ordered a whole bunch of different size post-it notes. Now, originally they were based on imperial measurements, but they're now defined. If you look at all the packaging, it'll specify in millimeters what you're looking at. And so here I've labeled them all up, and you will see the same measurements appearing over and over, and you will see pretty much exactly half that measurement again. So this one is 152, which is twice 76. And you've got 203, which is twice about 101.5. But oh, look at that, 101.5. So this one here is exactly half one of these. And what did I say? 152, that's half a 76. Look at these ones. They've got 76s. So it's the same halving scale. It turns out the post-it note scale, it is using the split property. It's also using the equal property, but it's not using the similarity property. And because it's not using the similarity property, as you keep halvening it, you alternate between two different families of similar shapes. And one set of similar shapes is pretty much exactly a 1.5 ratio. So if you were to line these up, they're exactly the same similar shape, and they are 1.5. However, it's not an exact half because the other ones are 1.34. There's a 1.34 ratio. And in fact, we can show you on the plot. This is where the P scale is. And so as you keep halving all the way down the P scale, you'll end up going between the 1.5 and the 1.34 ratios. All the way down, like including even these ridiculous little tiny ones. Why? Why do these have to be a descending scale based on the, like, why? I don't know. Don't know.
Meanwhile, back at the 512 A9s, I thought, for no real reason, I'd mix it up and start putting some on sideways.
And there is the finished piece. Now, you can see at the top there I got a little creative, and as well as doing one sideways, work of art, I've actually gone sideways, back up the right way, and then alternate all of those. And you can see over here I've done it the other way around, which means they don't quite mesh. Now if you're thinking, Matt, hang on, the whole point was to get 512 on here, and with all this empty space, all this bare A0 card poking out, clearly I wasn't able to get them all in. Well, you are very wrong. In fact, behind me, there are 514 A9s on an A0. In fact, if you just compare raw surface area of an A9 compared to an A0 and you divide one into the other, you can fit not 512, you can fit 519.724 of these in there. So hypothetically, if I got clever and rearranged them again, I could maybe fit in a couple more. But how many are possible? And what combinations of A paper give you the maximum overshoot? Hang on, I should go back a step here. So it turns out in the official ISO standard, where they define all the different A scale pieces of paper, you in theory work them out using the perfect idealized square root of 2, but then you round them. They are all rounded to the nearest millimeter, which, I think you round down. You get the idea. They're exact numbers of millimeters. And for the bigger ones, doesn't make a big difference. I mean, they're all slightly not root 2, but they're all pretty close. Who's gonna argue a few digits here and there? But once you get down to your A9s, indeed your A10s, it starts to make a big difference. So not only is this drifting greater and greater distances away from root 2, but it's getting smaller than it should be. And a millimeter off an A3, an A2, no one's going to notice that. But a millimeter or two off here, that makes a big difference. So this should be 37.1627 up and down, but it's not. We're losing that 0.1627, and it should be 26.2780 side to side, but it's not. We round it down. and those little rounding downs add up. And that's why across this many, because each one's ever so slightly smaller, you accumulate the spare space. You can kind of shuffle it over to one corner and you can get yourself a lot of extra wriggle room. Actually, if I come clean on this, so we've made this look more complicated than it needs to. These rows here that are up the same way, they could have all been down on top. I didn't have to do this. I'll explain why later, but for now it's just unnecessary. And then the only thing that's really different to this is we have these extra 3 rows that are side by side. Okay, so if I'd put in all the vertical ones together and neatly, you would have this much space at the top, which is more than enough room to fit in the traditional 2 more rows, each with 32 vertical pieces of A9. Look at all that spare space, top, bottom, and the sides. And if we compare that to 3 rows of landscape A9s, you can see it just fits in that same empty space. I mean, it's a little more snug, but it does go in, showing us that we can fit more. Although, technically, yes, if you were paper maxing, you could slide these across to the left. There's room for a few more vertical ones in there, but that's not the point. I wasn't optimizing it. I just wanted to show you can get more than 512. So by taking 64 off this way and putting on 66 that way, that's how I squeeze the extra 2 in there that we did. Now, you can be a lot more clever than that, and it turns out someone called Noel was. For those deep in the Mass Cinematic Universe, you may have come across Noel Friedrich from when I did a video about how Mr. Beast and other YouTubers have progress bars during their ad reads that don't move at a linear rate. And Noel went through and did some videos on their channel where they did weird things to fix it, like they speed ramped the video. So what's happening in the video is going at weird rates, but it's linearized the progress bar. Very funny stuff. I recently saw a video that Noel made about this. They realized that you're rounding down to get the A paper scale, and they set about seeing if they could fit the maximum number of A10s, so not A9s, the next one down, into an A0. Now, technically, you should be able to fit an extra 15.45. So instead of 1,024 A10s, you should be able to fit in 1,039 and a smidgen A10s. They weren't able to work out how to fit the full 1,039, but they were able to fit 1,038, which is just incredible. After I watched Noel's video, I was like, well, how hard can it be? I'm going to find my own packings. So I contacted my good friend, Matt Scroggs. Matt Scroggs and Scroggs did all the coding. I'll link to it on GitHub. Did a phenomenal, we were basically trying to find lazy ways to search orthogonal packings only to work out if you could fit more in. And our solution for A10s into A0s wasn't great. I mean, you might be thinking that's why I did the A9s, because the A10 one wasn't worth showing. No, I did the A10 one, here it is. So here, these are our, oh, you have no idea the human hours you're looking at right now. These are, there's 7 extra ones. So this is 1,031 A10s put into an A0. And you can see over here, there's our little cheeky offset at the top there in exactly the same style. However, it doesn't read quite as well on camera. It's a bit hard to spot what's going on. So here it's a bit more obvious. There's a little cheeky gap. Noel's solution, a lot more complicated. There's a lot more offsets. It looks like inclusions in like a crystal structure. And not only did they find that, but on top of that, they managed to prove there's definitely no orthogonal packing capable of fitting the full 1,039. There's some very cool visuals behind the proof. I will link to Noel's video below. Absolutely worth checking out.
Our code, which produced images like this that I used before, was not as efficient as Noel's code. We've already seen that you could fit more A9s into this without too much effort. We just wanted to show the existence of solutions where you could fit more in. And the actual arrangement here is a byproduct of the way Matthew Scroggs structured the search to try and make it achievable in a reasonably short amount of time. And while some people see inefficiencies, I see art. I really like this arrangement. I think it's got a really nice aesthetic look to it, and that's why I decided to exactly copy this when I was sticking my A9s onto A0. I wanted to create the exact artistic representation as its code creator intended.
Now, Noel didn't stop there, nor did we either, but Noel decided to exhaustively find every possible packing for all the situations. They're now all on Noel's GitHub. I'll link to that below. They're actually presenting their whole paper at a conference at the time of recording a month or two from now, and they will have an update video on their channel. Keep an eye out. Scroggs and I, however, also didn't stop there, but we went in a different direction. So the A paper scale famously goes from A0 to A10, but if you look at the actual ISO specification document, they do two bigger ones. So if you have two A0s together, we could think, well, it's going to be an A-1. No, they just call it a 2 A0. And the next one up that's equivalent to 4 A0s, they just call that a 4 A0. It's so embarrassing. Like, they were doing such a good job with the number system. If you subtract any two A scale numbers, that's the 2 to the power of that gives you how many fit. If the two A scale papers are the same parity, then they have the same orientation when you overlay them. If like one's odd and one's even, then they're at right angles, and they use 0. But then they stop at 0. They stop at nothing. They don't use -1 and -2. In theory, the A scale can keep going in the negative direction. And many years ago, many years ago, back when Twitter was fun, I had a viral tweet based on this.
If you continue the A4, A3 paper sizes, a piece of A34 paper would fit inside a human cell, and A-47 would be bigger than the Earth. Old Twitter.
So Scroggs kept going to smaller and smaller A paper sizes, and as you get smaller, that 1 millimeter rounding, ironically, gets bigger and bigger as a percentage, or at least as an impact on the paper. And so what I'm holding here is you're gonna struggle to see them. I've got a single A17 in yellow, and I have 3 blue A18s. Isn't that nuts? And so here, just to make it a little easier to see, I've got a white A8. So I'm gonna pop those on there. Oh goodness, they're all over the place. Oh, I've lost one. I've lost a single A18. Let me get that back on there. Okay, so now, don't worry, I'm gonna rearrange them with a pencil, but we have got a very expensive macro lens, so you can see a real close-up of what I'm doing here. So if I very carefully stack these A18s next to the yellow A17, you'll see, ooh, let me get this one. You'll see that 3 blue A18s equals 1 yellow A17. So now, I mean, we've violated the straight split. There's now a 3 to 1. It's 3 A18s equals 1 A17. And because we have to round to the nearest millimeter, these little tiny A18s, they're 1 millimeter by 2 millimeter, whereas the A17, that's 2 millimeters by 3 millimeters. So the ratio's all over the shop. We've now, on the A17, got a ratio of 1.5, no longer root 2, and on the tiny A18s, we've now got a ratio of just 2. Forget root 2. It's just regular 2. Isn't that ridiculous? I think you'll agree, worth us hiring that really fancy macro lens. All right, let's get the whole family back together again. So here's our entire A paper scale with the poster child. There is the mascot, A4. And now the family goes all the way down to our A17s and A18s. Although I will say A19, 1 millimeter by 1 millimeter. A20, 0. So technically, if you want to fit A20s into an A4, you can fit infinitely many. There you are. There's a bombshell finding. And there is one other big dramatic development that I'll do right at the end. But first, I want to thank the sponsor of this video, which is Jane Street, the financial company. They are promoting their WISE program. This is for women, transgender, any kind of gender expansive people. It's a multi-day program where you can see how Jane Street use things like maths, computer science, and probability concepts in trading. Applicants don't need to have any prior knowledge of finance to apply. They just need to be interested in seeing what it might be like to have a career in a quantitative trading firm. You don't even need to live in Hong Kong, New York, or London, where the WISE courses are based. Jane Street will cover all travel and accommodation costs. In fact, there are no costs at all to participate in this program. You just need to be a self-identifying woman, transgender, or gender-expansive person who is about to start their first year of university and has an interest in studying STEM. Applications for the WISE programs in all 3 Jane Street offices close soon. Hong Kong on the 31st of May, New York and London 14th of June. So if you think WISE is for you, or you know someone for whom it might be relevant, please do pass on the details from the description below. And if it's of no use to you or anyone you know at all, thanks for watching the promo anyway. And the final development, if you're looking for areas of future research, untapped, putting a paper in a paper research potential, is there are tolerances. I was reading through the ISO standard and you got plus or minus a decent amount. So our friends, the A18s barely exist because anything under 150 mil, you've got plus or minus 1.5 millimeters. Imagine taking your A9s and your A10s and subtracting an extra 1.5 millimeters in every direction off these. And once you get to big things like the A0, plus or minus 3 mil, which actually I discovered. These cards are a little bit, we only buy it in cardboard, a little bit shorter landscape than we expected. But there you are. So I reckon if you were to use the rounding tolerances, as in like the plus or minus give to your advantage, you could pack in even more. So there you are. Huge thanks to Noel Friedrich for making the original video and inspiring this one, and massive thanks to Matthew Scroggs for sitting down and coding up our ridiculous orthogonal solver. So thanks to you. Thanks for watching a video of someone putting 514 bits of paper on a bigger bit of paper.